welcome to the Podium podcast. Today, we are honored to have an expert guest with us to break down the engineering and physics of this everyday appliance, the microwave oven. He graduated with a summa cum laude distinction with a Bachelor of Science in Electrical Engineering at the Massachusetts Institute of Technology. He got his Master's in Metallurgical Engineering at Oxford University and obtained his PhD at Harvard University in Applied Physics. With numerous citations and dissertations that we cannot enumerate anymore because of time constraints, I want to introduce to you and welcome our distinguished guest, Dr. Catalino Espejo Jr.
Hey, thanks for having me again, Joanne. And I'm happy to be back on your show. It's been 5 years since I was last here? Anyways, I'm glad to be back on the #1 science-based podcast.
Thank you, Doctor. Can we start with the first question?
Of course.
In simple terms, what is a microwave and what does it actually do?
I mean, most people know what a microwave is already, but to put in simplest terms, a microwave is just a box that cooks food using invisible radio waves. Instead of heating up the air inside like a normal oven, it fires energy waves straight to your food, forcing the water molecules inside to spin billions of times a second. That intense friction from the molecules creates the heat that cooks your food incredibly fast.
That's very interesting. It feels like such a modern necessity, but where does it actually come from and who invented it?
Well, you wouldn't believe it, but it was actually invented by accident. Back in 1945, an engineer named Percy Spencer was building a military radar system for World War II. He was standing near an active radar and noticed it had completely melted a candy bar in his pocket. He tested popcorn kernels next. They started popping all over the lab, and then the microwave was born.
Wait, so early microwaves were just military radar parts?
Exactly. When the first commercial model kit hit the market in 1947, it was called the Radar Range, shown right here. It was an absolute monster, nearly 6 feet tall, weighing over 750 pounds. Because they were so massive and expensive, they were originally only used by luxury ships, passenger trains, and large restaurants. It took decades of manufacturing breakthroughs to shrink that giant tech down to a cheap countertop box that it is today.
That's very exciting trivia, Doc. So, before we get into the heavy physics, what are the main parts inside this box that make it happen? Like, if we opened one up, what are we looking at?
That's a great question, actually. From an engineering standpoint, it really comes down to a few core components. Let's look at the magnetron first, which is like the engine, a vacuum tube that converts electricity from your walls into those high-power cooking waves. So, if you were to look at my diagram here, this is the magnetron. And if we were to open this up, it would be here in the internal components. Secondly, we have the waveguide, which is a metallic channel that guides those waves straight from the magnetron into the cooking cavity, which is the internal metal box. So, from the magnetron, we have the wave pipe guide that guides that energy straight down into the cavity. So, it would be located around here at the top, and that energy goes all the way down here. Now, let's talk about the waves. First, we have the turntable to spin your food. Right here. And we have the Faraday shield, shown on the door. The Faraday shield is a metal mesh grid on the window that blocks the waves from escaping. So, here it is. And finally, the mechanical interlock switches on the door latch that act as your electrical safety cutoff. So, that would be found right here. And those are the main components of the microwave.
Oh, so those are all the hardware pieces. I definitely learned something new today. So moving on, how does all of that hardware actually work together to use the technology?
Yeah, so the magnetron generates the waves, and the waveguide pipe guides them in, and the metal walls trap them inside. Once those waves hit your food, they force the water molecules in your food to rotate violently back and forth. That rapid movement creates immense friction, and that friction is what generates the heat to cook your food.
Oh, that's very good to know. So let's talk about how it actually cooks the food. You mentioned it forces water molecules to spin. What's the physics behind that?
Yeah, it's a good question. This relies on a principle called dielectric heating. Most food is packed with water, and water molecules are naturally polar, meaning they have a positive side and a negative side, like a tiny chemical magnet. We call this a molecular dipole. When the microwave turns on, it floods the cabin with an invisible external electric field. This brings in a core physics formula, shown right here. So, F represents the force in newtons, Q is the electric charge in coulombs, E is the electric field strength at newtons per coulomb. This just states that an electrical field exerts a physical force on a charge. Because our water molecules are charged dipoles, this field applies a force that yanks them around, trying to make them line up with that field's direction.
Ah, so the molecules are constantly twisting to catch up with the field?
Exactly. But they're doing it at such an extreme speed. Microwaves are transverse electromagnetic waves, operating at about 2.45 gigahertz. That means that the electric field switches direction about 4.9 billion times every single second. So, if you look at the diagram here, you can see that the water molecules are trying to line up with the waves, but that's happening at 4.9 billion times a second. The water molecules inside your food spin back and forth to keep up. That high velocity of rotation creates massive friction between the molecules, and that friction is what generates the heat to cook your food. So, if you look at my diagram here again, you have all these molecules, and those waves are making the molecules collide with each other and create massive friction, meaning heat.
Wow, but I've also noticed that sometimes food cooks unevenly. One spot is boiling hot and another is totally frozen. Why does that happen?
That comes down to wave interference. See, the metal walls inside act as mirrors, reflecting the waves back into the cabinet. As they bounce around, they crash into oncoming waves, creating an interference called a standing wave. Luckily, I have a diagram for that. So here we have a diagram of the standing wave. This wave pattern is completely locked and frozen in place, which creates two distinct zones. Antinodes, the ultimate hotspots, and the nodes, the cold spots. So, if we look here, we have the nodes, cold spots, antinodes, hot spots. Because these hot and cold spots can't move, a rotating turntable is needed to move your food through them so it heats evenly. So, let's take a look at our microwave. So, the reason that the turntable is here is because if we just left it and it's not moving, then you're gonna have one really hot spot on one really cold spot. So, you need the turntable to move your food so it hits it evenly.
It makes so much sense now. I think I'm finally starting to get it. So now, if these waves are powerful enough to boil water through friction, how are we safe standing right next to it? Why doesn't it cook us? What are the risks here and how are they managed?
Yeah, so a primary risk with 2.45 gigahertz radiation is thermal burns to human tissue. Our eyes are especially vulnerable because they don't have great blood flow to cool themselves down. So leaking radiation could cause cataracts. So, cataract radioshantis, aka induced cataract, could happen from the radiation from your microwave. But these risks are managed by pure safety engineering. First, the viewing window has the metal mesh grid called a Faraday shield. So, we look back on our microwave, the mesh inside, the Faraday shield. The holes on the mesh are about 1 millimeter wide. Because cooking waves have a physical wavelength of about 12.2 centimeters, they are way too big to pass through the mesh and bounce right back inside. Meanwhile, visible light waves can still pass right through and let you watch your food cook. Second, to manage the risk of someone opening the door while it's running, safety laws require dual mechanism interlock switches and a latch. So, let's take a look back. These are the switches. So, the exact millisecond that you pull the door handle, the circuit breaks and instantly stops all wave production before you can be exposed to the radiation, and that's what keeps us safe.
Okay. It's honestly so incredible how much safety engineering goes into the kitchen appliance. So looking at the bigger picture, how does this microwave technology actually benefit society as a whole?
Honestly, the benefits are huge. It completely changed the rhythm of modern day technology. For one, it's energy efficient. If you think about a traditional oven, you're wasting a ton of electricity just heating up the air and the insulation before the heat even touches your food. Microwaves completely bypass all of that waste by targeting the water molecules directly. And because it cooks so fast, with barely any water, it's actually way better for you nutritionally. When you boil or bake vegetables, for example, for a long time, heat-sensitive vitamins such as vitamins B and C break down. Microwaves lock those nutrients in. But really, the biggest impact is just pure convenience and accessibility. It enabled busy families, students, and workplaces to prep a hot, safe meal in just a couple of minutes. It honestly probably saved the world billions of hours in household chores.
I agree with that. So to wrap things up, we know microwaves are in almost every kitchen. But is this wave technology used anywhere else in society that might surprise people?
I'm glad you asked. And yes, that is true. This exact microwave radiation technology is used way beyond the kitchen. So, let's look here. Your cell phone networks, Bluetooth devices, and Wi-Fi routers all transmit data using lower power microwave frequencies to connect you to the internet. So, if you look here, local wireless networks, telecommunications, aviation and military radar, which I will get to in right now. Aviation and military radar systems use them to map weather and track aircraft. And industrial factories even use high-power microwaves to rapidly dry wood, paper, and textiles. It's one of the foundations of modern technology.
It turns out a lot of world-changing physics is hiding right inside our kitchens. Thank you for breaking it down with us.
Hey, anytime. Thanks for having me.
I don't know about you guys, but I definitely learned a lot about today. So that concludes our episode of the Microwave Oven. Thank you so much for coming with us and speaking today, Dr. Catalino Espiritu Jr.
Oh, the pleasure's all mine.
And before we go, please subscribe, hit the like, and post notification button. See you next week on the #1 science-based podcast of the world, the Pro EDM Show.
On which the science of today is the technology of tomorrow.